morning, everybody. My name is Dave Kolesar, and I'm here to talk about all digital radio. AM radio will probably happen first in all digital before FM. FM has significant market share. AM is struggling. It's more ripe for disruption. So WWFD, there we go. All digital AM is a cooperative effort. Hubbard Radio, our parent company, Xperi Corporation, also Kintronics Laboratories, who did a lot of the design and modeling work for the modifications of our antenna system. Cavell Mertz, I'd like to thank Gary Cavell in particular for all the hand-holding that this project required, and also for writing the experimental authorization so that we could get on the air with this. Also the transmitter manufacturers, Nautel, BE, and Gates, each contributing to this effort to make it work. Potomac Instruments helping make sure that everything is calibrated and measured. And of course NAB Pilot for the test plan. Why do we do this? You may say, well, AM already has a digital mode, which is the hybrid mode, and that's true. There's the analog signal and the digital is on the side. Taking a look at it, it requires plus or minus 15 kilohertz of bandwidth from your center frequency. Unfortunately, the digital carriers need to be 30 dB down from your analog, and that gives you a lot of problems in terms of robustness. So, looking at the MA3 waveform, first thing we'll notice is that it's a bit spectrally more efficient. It's plus or minus 10 kilohertz. So by migrating to that, you're taking up less bandwidth. Also, your digital power is your licensed power. All of your licensed power goes into your digital carriers, which makes it a lot more robust. And this alone is a reason to consider.
Yep. I mean, the one thing about the MA3 waveform is, as Dave said, that all your licensed power can be in the digital primary carriers. It does, and we'll get into that later, does increase your spectral density quite a bit. So you're going to have to recalibrate your whole system, measuring from analog power to digital power, because it is going to be different.
Of course, to answer the question, why do we do it, a picture is worth 1,000 words, and this is a picture of WWFD as received on a pre-production Audi A8 earlier this week. First thing you'll notice is there's title, artist, and album, and there's also album art, in this case being recalled from the internal Grace Note database in the receiver. But with the MA3 data service, you can transmit album art via the data service artist experience. So in the year 2018, this is what broadcasters are expected to provide in the dashboard. Analog AM doesn't do this. Hybrid AM doesn't do this well. So all digital gives you both aural and visual parity with other services that are already in the dash. This is WWFD. It's a two-tower array. It's 4.3 kilowatts daytime, non-directional out of one tower, 460 watts a night, directional, series fed. And the story of the MA3 conversion starts at CES 2017 when I approached Xperi at the trade show and asked for assistance and advice on converting this station here to the MA3 mode. What that entails, of course, is the evaluation of our antenna system and modification, the transmitter installation and its setup, achieving the experimental authority, and of course sign on and our initial drive testing. We'll talk about that as well. A station transmitting the hybrid mode, it should be said, first of all, needs no modification to its antenna system to go all digital. If you're doing hybrid HD right now, you can do all digital. A quick rule of thumb is that if you have an SWR 1.4 to 1 plus or minus 15 kilohertz from center channel, you can do both MA1 and MA3 with the all digital mode. If you recall, the bandwidth for MA3 is actually less. So when you get, so if you want to do the MA3 mode, this rule of thumb then becomes 1.4 to 1 at 10 kilohertz. So it is possible for a broadcaster who is not able to do the hybrid mode to be able to do the all digital mode.
But it is ideal to get that 1.4 to 1. You kind of want to shoot for that. That's really the kind of gold standard that you have to go for.
Yes. So, taking a look at what we had before, it was a mess. This may be typical of what you find in an AM broadcast station that hasn't had much love in recent times. A 1.8 to 1 SWR at 10 kilohertz a day, 2.1 to 1 at 10 kilohertz at night. Not very good. This was bad enough to impede our analog audio bandwidth. Of course, the issue was not noticed because as the audio bandwidth of receivers have degraded over recent years, you don't necessarily notice the fact that your antenna system has degraded as well, because you don't have a receiver to pass it anyways. So a few notes about WWFD. The towers are short. They're 73.5 degrees tall with some top loading. There's also some pass reject filters for a station less than a mile down the road at 110 kilohertz away. The station is also a diplex on 1670 for Ubiquity's experimental station. And there are RPU and STL antennas on one of the towers. So these are typical issues that a broadcaster may encounter, and which of course gave us some problems along the way. And I want to talk about just the typical experiences, how our experience may be typical of a broadcaster doing the conversion. The daytime network is very simple. Transmitter, ATU, filters, and antenna. Starting with one of the original sins of the station, about 20 or 30 years ago, the transmitter was moved from next to the phaser to another room. So we had about 30, 40 feet of transmission line, which added some inductive reactance in the system. So we had to add a capacitor to tune that out. And these are things that, of course, as we started to tune up, and I'll talk about later, we noticed. So, of note here, the other tower simply floats at 820 kilohertz during the day. So this is really just a one tower system. At night, it's a simple power divider and a phase shifter with our ATUs and filters and pass reject filters after each ATU. And this is the basic design of the system, pretty typical in any standard AM direction. So what do we need to do to prepare for antenna modification? you need to document everything. We measured all of the values in the phaser and the ATUs, all of our component values. We measured our self and drive point impedances, and that's very important. You want to make sure your schematic is correct and your antenna monitor and your base current meters are calibrated and accurate. What you're going to do is you're going to give all of this data to a company, Kintronics in this case, to model what's there. And what they'll do is the model that they create, they'll model what's there, how well it can perform, and what needs to be changed if necessary in order to pass all digital. And of course, some modifications were necessary, but first we had to do some optimizations. Here's where you'll find at what may be typical in stations, a lot of sins that have gone, I guess you could say sins of neglect. Our pass reject filters after the ATUs had, they were mistuned. As the environment around the towers have changed, construction, degradation of the ground system, et cetera, the filter networks may go out of tune. So much so that one tower was adding one filter was adding 16 ohms of inductive reactance, and the other was adding 6. So these are things that your ATUs were tuning into. And of course, that was affecting the bandwidth of the system. So that needed to be corrected. And that may be an issue that any broadcaster may face as well. Taking a look at our RPU and STL antennas.
This is where the biggest sin occurred. And this happened after a very frustrating afternoon of beating our heads against a wall with a computer that wanted to reboot. Every single time we were doing our measurements with a box called Array Solutions. It's Power Aim. Basically, it's a network analyzer on a computer. We were just having dickens of a time with it. It was 90 degrees. It was humid. We were just sweaty. We were tired. And Dave saw this.
Yeah, you just stare at the wall, and occasionally staring at the wall pays off. An RPU line was abandoned years ago before our company bought the signal. That RPU line had an isocoupler on it, which was bonded to the tower feed point. When that isocoupler was ripped out, the line became unbonded, so we had a capacitor across the base insulator, which of course affected how well the system was and could perform. So we needed to get rid of that, and so we added a strap to bond the transmission line to the feed point. Things that are very simple, but things that went unnoticed for probably 30 years. I believe what happened was the engineer 30 years ago ripped out the isocoupler, saw the directional parameters had gone out of whack, and just cranked on the phaser until things came back in. That's probably pretty common. And of course, that adversely affected stability.
Yep, and then when the phaser ran out of room, you ran the coils to the stops. Okay, we'll just run out to the ATU, put another turn in at the ATU coil. So all these sins were just compounding one on top of each other and on top of each other on top of each other. This was 30 years of neglect. We just kept simply finding one little thing after another. But with the RPU line unbounded like that, there was no hope of the array ever getting into parameter. There was just no hope.
So taking a look inside the phaser cabinet, the phaser had been modified over the years. It's actually the third phaser in its 1961 cabinet. Originally the station was on 1370, daytime only. In 1987, a nighttime mode was added and the frequency was shifted to 820. One tower marched its way across the lot to reorient the two. Sections were bolted on top, and top loading was added as well. But inside the phaser, that meant that A day mode just simply had to pass through it, a long piece of tubing, which interacted with everything in the night network. So if you have, especially a modified system, as probably a lot of you do, you need to make sure that things are isolated. So we ended up putting shielded transmission lines everywhere where there was a long piece of tubing. And that's just part of best practices. So, correcting the sins, we can move on to actually doing the modifications that were suggested by Kintronics. At our ATUs, we had L networks, we converted them to Ts. We did that because you have more flexibility in design for bandwidth and impedance matching. Inside the phaser cabinet, we converted our T networks to series L.C networks, which are simpler. They don't have as much adjustment, but they're much wider bandwidth. So what ends up happening is that most of your phase shifting, of course, happens in your ATUs, and your phaser becomes a fine-tuning control. So, tuning up the daytime network, because we did this first because it's easier. You tune for 50 plus J0 at the transmitter. And when we did that, we ended up with much better performance with the new networks than we had before. What should be of note, if you can squint and read this, is that the SWR is still a little on the high side at 805 kilohertz, which means the array might be marginal on MA1, but with MA3 it should pass it no problem. Moving on to the nighttime antenna system. This took a while. This was a learning experience for us. But if you take a look at what I've got written on this slide here, you'll recognize this is just the standard procedure of tuning up any AM array. A good reference, of course, is Jack Layton's book, Directional Antennas Made Simple, if any of you have it. If you want to go into some more detail, read Edmund Laporte's 1952 tome, Radio Antenna Engineering. I found a copy online and bought that and read that cover to cover. Quite a good book. Basically what you want to do is you need to get 50 J0 at the input to the phaser and at the output to each transmission line to the tower. And we were nowhere close to that before because of the previous sins that we had to correct. So when we do that, we end up with a network that's just about as good as the day, which, given our previous experience with the array, was quite a miracle. These, of course, were all done with the Array Systems powering.
Yep. Very handy tool if you've got an AM directional. Very handy tool.
So at this point, I'll hand it off to Mike Raide to talk about the transmitters.
Okay. So for the transmitter, what they originally had for the main was a Harris, which is now Gates Air, Gates 5. They had the backup as a Nautel AMFET 5. That had to be removed, pushed to the side, quite literally in the transmitter room. We ended up getting a Broadcast Electronics AM6A to install as the new main. The Gates 5 would be relegated to backup service, although it's a very capable, you could almost call it a co-main. Then you needed W load handling, the digital modulation, install that outdoors, because obviously that's going to kick off a lot of heat, especially in MA3, where the spectral density, once again, is a lot higher. So this is what we came up with for configuration. Currently, right now, we're using, for the main system, we're using a Nautel Multicast Plus importer and a Nautel Exporter Plus. The multicast importer, it can do The importer-exporter is our new Gen 4 platform. So it does do importer-exporter functions. Currently, we don't have a commercial release of AM or an MA3 or MA1 mode for the Gen 4 exporter, so this is why we install the Exporter Plus. Then we use a Nautel AM IBOC exciter, which is a standalone IBOC RF generator with the XGen, our XGen system installed to provide the, excuse me, the low power oscillator feed. Instead of using the internal oscillator, we're now using the external oscillator. BE has a little converter pad to do an external oscillator. Way back when the AM series was originally designed, the considerations were for AM stereo, not AM all digital. But the concept is still the same. It needed an external exciter. For the backup is just a BE ASI-10, a standard Gen 2 exciter. It's the older version, no longer manufactured. The motherboards have gone a DMS long ago. But that feeds right the magnitude phase. Once again, slight modification needs to be made to the Gates 5 to accept an external oscillator. And the magnitude goes in. And the magnitude for both, basically for the main and the backup, the magnitude is just the audio input, and it's the left channel audio input. And then that's all that's needed for that. Okay. Transmitter testing and tuning. The best thing to do is if that manufacturer has a guide for turning up MA1, follow that guide to the letter. They've done all the research on it. They know their transmitter better than anybody else. And I know all three, or the big three, Nautel, Gates Air, and BE have manuals on how to do this. It takes about a morning, probably 4 hours. Just go through it step by step. Once you get it working in MA1 properly, with meeting the NRSC 5 spectral mask, which is a spectral regrowth on the sidebands, 25 kc out, need to be 65 dB down. The spectral regrowth beyond 15, either side needs to be 65 dB down. Once you get that spectral regrowth down to where that is, literally it is just going into the exciter, telling it to go from MA1 to MA3. In some instances, like the Nautel AM IBOC, it automatically configures the IQ scale factor for the proper setting. In the ASI-10, you're going to need to set that IQ scale factor, which basically sets the power from 12,000 to 6,000. You're basically cutting it in half. The older Gates Air Dexstar does the same thing. It does it automatically. So when you tell it to go to MA3, it sets the mode automatically. It literally is just switching modes, and in the Nautel's case, didn't even require a reboot. It literally just hit the button, bam, it's spitting out an MA3 signal. You just slightly readjust your parameters to accommodate MA3, but your mag phase delay is, which is the delay between the magnitude component and the phase component. The magnitude is the audio component, the phase is the actual RF square wave RF generator. And that adjusts the time difference between the two to make sure that they're properly aligned, and that lowers your spectral regrowth to the optimum level. You just have to do your IQ scale factor, just a slight adjustment, probably no more than 10 samples, which is, I'm going to get this wrong, I know I am, so forgive me, Paul and Harvey. I think it's 23 microseconds, I can't remember. But so once you get that set, you're going to look at your spectrum analyzer, make sure the regrowth is down, and then you're going to need to calibrate your transmitter a power meter. It's going to look like you're spitting out, at 4,300 watts, it showed about 7 kilowatts on the transmitter, which was, the transmitter was just going nuts at that point. So what you have to do is you have to look at it on a spectrum analyzer, unmodulated signal, and adjust your power down to 4,300 watts, and take a channel power measurement. What you do, you take your analog unmodulated carrier and measure 4,300 watts. Take a channel power measurement on your spectrum analyzer, and then go ahead and turn on MA3. Then you lower the power output on the transmitter to match that channel power reading with the unmodulated carrier. And that's how you very easily and properly can adjust the power output. So is this where you wanted to talk? Or the grant of the experimental authorization from MA3 mode was granted on a 1-year experimental period. And it was we were allowed to commence operations on July 16th of this year. And then here we all are on that very fateful day, July 16th at noon. Dave played an announcement basically telling the listeners that if they were listening and if they had an HD radio, that they would hear a rush of static for a few seconds, silence, and then the regular program would come up as normal. So at that point, we turned on AML Digital. The afternoon was spent just adjusting, making sure everything was in parameter, verifying the base currents, directional parameters. We went out and did monitor points we put it in night pattern, so we did the monitor points. And at that point, we started commencing our driving. So off we go with a test radio and our logging program. Excuse me. So for MA drive testing, under ideal circumstances, the core mode can be decoded down to the 0.1 millivolt contour in the day. We have had reception reports at or near the 0.1 in Harrisburg. When I did my initial drive testing, I drove north through the city of Harrisburg, encountering 2 or 3 dropouts on my car radio, which is a 2011 Ford Escape. I didn't get a loss of real listenable service until Duncannon, PA. That's over 70 miles away. Dave was out in Cambridge, Maryland. Cambridge is, let's see, do we have a laser pointer? Yeah. Cambridge, Maryland is right here. Duncannon is like right here. And Dave was able to get in the parking lot of a hotel that he was staying at in Cambridge, WWFD. So nighttime reception seems to be possible beyond the NIF as well. The NIF, as many of you all know, is the nighttime interference-free contour, which is 4 millivolts. Reception is possible. I've driven the nighttime to the 0.5 here in Eldersburg and beyond to Randallstown and still receive the station. So the MA3 is very robust. Usually to the 0.1 of an analog AM station, you're going to hear a lot of noise, and it's going to be very objectionable. In some cases, sometimes you may hear very faint audio, but you'll hear the heterodyne of the analog carrier, and that's all you'll hear. At the 0.1, you're going to get a digital lock. So here is the initial drive test that I did. This is out to the 30-mile radius out here. There's the initial Harrisburg North run. I took this all the way out to just about Sidling Hill is where I lost it here. If anybody are familiar with Maryland or Western Maryland, this stretch right here is very, very hilly. It's actually mountainous. You're going through several mountain ranges, going through the Catoctin Mountains. So you're getting a lot of peaks and a lot of valleys. These little blips that you're seeing here are grounded conductive structures. It has nothing to do with terrain at all. So the ground wave works very well even in the highest terrain. To the west or to the east, we saw a little less performance, especially getting it towards more populated areas here at Ellicott City, which is just a suburb of Baltimore. Columbia, where our office is here. We do get the station in Columbia. We get it at our at our office in the parking lot. I get it in my car. Several of my coworkers all get it. I can listen to it from Columbia, drive north, and then I live out here in Libertytown. I have 3 dropouts the whole trip, and that's a 42-mile trip. Getting down here, this is the important one, because this is where you see a huge population center, and as you can see, we got good reception all the way down to Bethesda, which is very impressive for this station, since this station really is not intended to get that kind of coverage. Okay. So outstanding issues, MA3 secondary carriers do not have enough CD over N naught to lock at the receiver. That's an issue that we're working through with the manufacturer. As a matter of fact, I plan a trip out there in a couple weeks. Documentation of the effects of noise versus signal, robustness, and useful coverage. Power line, electrical storms, and indoor noise environments do affect the MA3 signal. So we're going to need to look at improvement there.